Hello, my name is Vincent Piscuzzi. I'm going to talk today about some work on a proof of concept performance portable SYCL-based fast Fourier transformation library that I did with Mehdi Dukoli from CodePlay. Start by setting the scene a little bit, talking about the Department of Energy in the US HPC systems, which have gone through tremendous improvements in terms of computation, storage, and so on over the last 10 years or so. So in 2013, we're looking at really, around the order of 10 petaflops, and these systems were all homogeneous in nature, so x86 pretty much, and really a single programming language, C++, C, Fortran, would be used to write your applications. Going forward to 2018 and more recently, you have these heterogeneous systems comprising CPUs, GPUs, and then even more exotic hardware eventually, which you can't just program them all using your C, C++, Fortran anymore. They rely on different programming models in order to leverage the full capabilities of these machines. So it is for these reasons and others that I generally classify these two sets of systems as easy on the left, which corresponds to homogeneous systems, and then hard on the right, loosely speaking, heterogeneous systems. I need to say this work all started from the U.S. Department of Energy's High Energy Physics Center for Computational Excellence, or HEP-CCE, which comprises 6 or so different high energy physics experiments ranging from Collider at the LHC, so ATLAS and CMS, to cosmological experiments, to neutrino physics. And really what we're trying to do here is investigate performance portability, improvements in how we can do our input-output, complex workflows, so this is the large scale, kind of all-encompassing computational needs that we require for our experiment, and event generators, which typically has been historically a theorist's playground, but now with these big machines coming online in the US and elsewhere, experimentalists are getting their hands dirty as well and looking into performance portability to execute these softwares. So the Portable Parallelization Strategies group, which this work stemmed out of, it focuses on, of course, performance portability and for current and future high energy physics software. So what we do here is that we select among the experiments that in this green box at the top, we select some test beds that we can run standalone outside of the experiment's software infrastructure or framework, and we rewrite the C, C++ codes in using, say, CUDA, OpenMP, SYCL, Cocos, what have you. And we do some evaluation on each of these. Some metrics are ease of porting, of course performance is a big one, and where these systems or where these applications are able to run. So the reason we're doing this is because we're physicists, and we have a limited number of developers, people who are actually able to write the codes for these machines, and so we have large code bases, anywhere from hundreds of thousands to millions of lines of code that have to stand the test of time. So we're talking order of a decade, and we can't afford to rewrite our codes to target each of these different machines. We are also we also need to leverage these machines. They're coming up in the US. We're not going back to cluster-based computing, I don't think, anytime soon. And also, you see these images here where we're not just focusing on, say, the machines that are in the US, because these experiments are international collaborations. So we have machines in Finland, Italy, and they all have different platforms and architectures. So the motivation here is to look at different portability APIs, such as SYCL, and in this work, of course, we're looking at SYCL-based libraries. Why this is important is that you can decouple these from vendors, and which write libraries for their hardware specifically, and then you have to maintain multiple copies of the same hardware. You have to rewrite it, but it also removes the need for this boilerplate code when you're using interoperability. So this could add a bunch of if-defs and other pre-processing macros to say, if I'm running on this machine, do this. If I'm running on this machine, do that. And I'm not putting down interoperability. I think it's a great functionality, but ultimately what we want to do is to be completely decoupled from these two things. These libraries can also improve readability, maintainability, and sustainability, so you don't have some code that's generated by some very niche group. And it fosters inclusivity, so you can have community-driven open source projects where everybody can be involved and improve upon the existing code bases. What's more is that with recent C++ code, you can have template metaprogramming, which allow you to do further optimizations of your libraries depending on where you're running them. Even auto-tuning mechanisms where you can say, what device am I running on, and make either compile time or runtime decisions on how to best execute that code. And something that's important for us, for me, and I would say most sciences, is the reproducibility. So if you're running different vendors' libraries, ultimately you're gonna have different results. And when you're in the context of high energy physics, where you're doing very precise, high precision measurements of a given physical process, you need to make sure that whatever you're simulating or whatever data you're working with is consistent across wherever you want, whatever machines you're running on. So this brings us to performance portability. We take typically we've adopted the definition from the meeting in 2016, but also that of Pennycook, where you can say, from a performance perspective, it either runs yes or no, it's binary. But then you could extend that a little bit and say, does it run efficiently with respect to some baseline, which generally would be your native or vendor supplied library. Portability is whether or not it can execute on multiple systems and adapt, if your programming model can adapt to the varying architectures. So I give an example from the Pennycook link at the bottom here, where they define performance portability based on this expression here, where effectively if you cannot run on a single machine in some set H of machines, you get a performance portability score of 0. This is a stringent requirement, so I think it could be relaxed in some sense, but I think this really captures what the goals here for portability APIs and SYCL. Then on the other side of this green line is the productivity, so not as it's more subjective, I suppose, and then reproducibility, which I mentioned already, which is again very important for most, if not all, sciences. So the SYCL FFT is the work that we did for this workshop. We based our implementation naturally off of Kulituki, which I have some more information on, and kind of like an FFT 101 in the backup, but for the interest of time, I don't mention it here. We implement the radix 248 algorithms. It's a header-only library, so I give the interface here in the blue code. It's a functor templated class with 3 template arguments, which are the work group size, so depending on the hardware that you're using, work group factor, which depends on the input sequence length and then is determined on the host a priori, so before the calculations of the FFT actually happen, and then your SYCL language version, which allows you to make use of newer features in more recent versions of the SYCL spec. So I have to admit, this is very much a proof of concept work. Just as part of the HPC effort, we have the need for FFTs. So currently it's limited to one-dimensional inputs, does complex to complex, and and up to 2 to the 11 in input length. We don't do any in-place computations. Everything is out of place, so you have this extra bit of memory that's required to actually do the computations. The experimental setup, so all these machines, I am 99.9% sure were available to us through the Argonne National Lab Joint Laboratory for Systems Evaluation. So we run on 5 different architectures, ARM, CPU, an Intel CPU, AMD GPU, an NVIDIA GPU, and an integrated Intel Iris GPU. We show the maximum work group sizes here because ultimately this, in its current implementation, defines the size or determines the size of the FFT that can actually be calculated. So for example, the ARM Neoverse can do up to 2 to the 12 instead of 2 to the 11 as it is. It wouldn't be much work to extend this, but for another time. And then the different backends, so this is, how are we actually doing what's the offload mechanism. For ARM we used POCL, and then for the Intel we use OpenCL3 or TBB depending on if we're running with SYCL or 1MKL. AMD is HIP 4.2.0, and CUDA is PTX64, and Iris is OpenCL3. We use a range of compilers, anywhere, going from Compute CPP to ARM Clang, depending if we're running the native ARM performance library or our SYCL FFT. We also make use of Intel's LLVM based on the SYCL nightlies that are shown here, NBC C11.5, and then we compare our work with the native library shown in the last column. There is no, as far as I'm aware, there is no native, quote unquote, native library for the Gen 9 integrated GPU. So there's no comparison that can be drawn there. We just show the results of our library. Computational performance on Ampere and CDNA. In the green is an A100, in the red is an MI100. And we plot here the total time on the left it takes to do the forward transformation and the inverse transformation in microseconds. And this is these are shown as a function of the sequence length, so that's the input or the FFT length that you want to calculate. On the left is the smallest complete execution time, so this includes kernel dispatch plus execution, whereas on the right we show the smallest kernel execution only, so this removes the kernel dispatch, which I'll talk about a little bit later. And in general we see a consistent trend for both these hardwares, namely on the left they're mostly flat across the entire sequence length. The SYCL FFT implementations are the dashed lines in both figures, and we can see that there is an overhead induced by the kernel dispatch on the left, whereas if we disregard that on the right, in both cases we take numbers straight out of the profiling tools that are available for these hardware. You can see that SYCL FFT is not much worse off than ROC FFT, but we still do have some overhead running on A100s. But again, these are very small scale FFTs, and I think really it'd be nice to see what happens once we go larger and into multiple dimensions. Here's the computational performance for RISC, so the ARM, Intel x86, and Gen 9 integrated GPU. We were same things are being plotted. The forward plus inverse on the y-axis and sequence length on the x. We were quite surprised by the ARM, our SYCL implementation on the ARM CPU. This is shown in the gray curves on the left two plots. You can see there's significant overheads when we consider the dispatch, which again was quite surprising. If we disregard them on the bottom, in the bottom plot we disregard the dispatch, you still see significant overheads in the ARM executing on the ARM CPU, whereas the Intel x86 CPU Again, there's a constant overhead when you include the kernel dispatch as well as the execution. But when you disregard the dispatch time is in the bottom left plot, you can see that this is the performance of SYCL FFT is very much very close to the native 1 MKL. Again, much to be seen and determined when we actually go into larger FFT sizes. And then lastly, on the right is the Intel, the integrated Intel GPU, an Iris P580, which shows in the solid line the dispatch plus kernel execution, and then the dash line the kernel execution only. And again, a big hit in the dispatch. And these are small. These are small kernels, but nevertheless, you see at 2 to the 10, 2 to the 11, we have these significant spikes when including the dispatch versus just the kernel. For reproducibility, again, emphasis is on this. We look at the reduced chi-squared between the two distributions. The two distributions being SYCL FFT and the native library, and we show the difference on the top left for SYCL FFT and cuFFT. On the top right, SYCL FFT with HIP FFT or ROC FFT. Bottom left with ARM, and bottom right with 1 MKL. And without getting into too much detail about this, the take home here really is we're looking at single precision floating point numbers in our calculations. And so we see that in each of these cases, the results are reproducible or consistent to the precision that we're interested in. So finally, to conclude, the motivation here is, I guess, well, twofold. One is for HEP-CCE, of course, but also, we want this work to kind of seed and help grow the SYCL ecosystem. To have more SYCL-based, purely SYCL-based libraries. Again, decoupling from vendors, improving readability, fostering community involvement and contributions, as opposed to something that can only be run by a very small group of people who know how to, say, run the code generation tools. The proof of concept SYCL FFT, again, it has its limitations, but we are planning on extending this and also opening up to the wider community for other contributions. To our knowledge, this was the first demonstration of Intel LLVM's HIP backend, which did show, as we saw, a very good performance with respect to ROC FFT when considering kernel runtimes only. It's obvious that the small kernels suffer from launch latencies, but also these latencies or these overheads for dispatch are extremely sporadic and fluctuate highly on the hardware, on some of the hardware, which I could show in the backup slides. For ongoing and future work, we continue to improve on the SYCL, or we hope continued improvements are made to the SYCL backend implementations. In particular for offloading the calculations, because for us anyhow, we haven't in high energy physics, we haven't really gotten to the point where we can combine large sets of large we can't combine our functions in such a way that we can produce these very large or more demanding kernels. So it may be unfortunate that we're kind of stuck with these smallish, on the order of hundreds of microseconds or 1,000 microseconds, 1 millisecond, which we're going to pay the penalty for. We're going to pay the cost in these overheads. So yeah, we plan on supporting multidimensional FFTs and accommodating arbitrary input sizes. And one thing that we left out of this, and really it was just in the interest of time again, was taking a look at HIP-SYCL, because in our previous work we noted that the HIP-SYCL compiler was great with its highly optimized HIP backend. So it'd be interesting to see what kind of improvements we get with the MI100 and other AMD cards when using HPSYCL. So that's the end of my talk. I will continue now just quickly on the, almost the most important thing. Special thanks to our friends, our colleagues at Argonne Lab, National Laboratory, namely Benjamin Allen, Killian Kumaran, and Kevin Harms for all their support in helping us get access to these machines that we're able to demonstrate our work running on, and providing us with support whenever we had an issue. Or like, these guys are great, so shout out to those guys. And then backup. This is just auxiliary material, so it's FFT 101 is not important, but the auxiliary figures in the appendix of our paper. This shows, in the top right, a chart, a table of the different devices we used, the compiler plus their backends, and then the observed launch latencies. And this is a mean, or a rough estimate of the range. And we see the figures speak volumes. For the A100 and MI100 cards, they're pretty consistent. I mean, eventually in the MI100 you get probably some throttling because of the heating and of the machine as it's running 1,000 iterations of a given FFT. The CUDA or the NVIDIA device, the A100, was pretty solid across 1,000 iterations. Again, these are all separate machines, so there could be other factors playing, but nevertheless, the A100 performed very well. The ARM CPU up to about 500, the 500th iteration, also performs steadily, and then eventually the heating, I think, causes these significant fluctuations in the dispatch or the kernel execution. And then another solid device was the Intel CPU, which again is mostly flat across the entire range, or all the iterations that we ran. And an interesting one is the Intel integrated GPU, where you have kind of like this sinusoidal shape to the time of the execution time, and even like a huge dip at around the 500th iteration of the 1,000 that we ran. So I mean, this is all stuff that I'd be very interested to learn more about, to delve deeper into understanding what makes this, the fundamental reason why these things occur. But hopefully somebody at this workshop can shed some light on that for me. And that's everything for real now. Thank you very much, and I hope everyone has a great workshop.